So how many of you guys have at some point written a program that writes another program, prints out lines of code and then evaluates it? Probably, typical reasons are because it's tedious and repetitive, and you don't really, you don't want to write the same thing 20 different times. So I think most people find themselves doing this at some point, and so metaprogramming. One of the things you can get away with metaprogramming is that you can avoid having that be some sort of external process where you actually have to run one program and then, generate another one explicitly from it. So, the typical example is something along the lines of, let's say I want to define, I don't know, I want to, I have, let's actually look at some of the Julia source code. Oh, this is one of these distributors.
Just open up another terminal and look at it. I'll give you something that you like. Just go to tell that Julia.
Oh, okay.
Slash Julia, and you'll have the source code and
slash Julia. Okay. Okay, yes. I am used to having source code available. Okay. What do you use for an editor on this thing?
You can use VI.
Oh, great.
Emacs.
Emacs is better. I'm going to use Nano. I'm super ghetto like this. So here's a good example. This is why demos are nice on your own machine. Okay, so.
You're trying to find the vectorized?
Yeah, I'm just trying to give some examples of where we do lots of evaluations.
Just open up LAPACK.jl.
Okay.
That's the easiest one.
Okay. Okay. So here's a situation where in the Julia source code, we have to do a lot of calls to LAPACK, and they end up looking all exactly the same. Except they have slightly different names. So instead of, what a lot of systems would do is they would actually have a script that prints the code and then evaluates that code that has been printed. But it complicates things because, now you need two different programs instead of one. It also means you need a build step that generates the code first. This is, so one of the goals here is that in Julia you really shouldn't need a separate build step. What you do is you actually write code that generates code that you then immediately evaluate. So I'm going to explain how that works. This is kind of scary looking, but it's actually very straightforward.
You could open class.jl for simpler examples.
Yeah, okay. I'm just going to do a couple of examples. So
there's really two concepts here. One is code generation, and the other is calling outside functions.
Mm-hmm. Yeah. So the basic example is, let's say we have we want to have a function that looks kind of like, function foo that takes a number n and does this. It prints print line foo, except we want to do it n times. Okay, so now we can call function foo 5, and it prints foo 5 times. Totally contrived, ridiculous example, but I'm going to show you what we can do. So now let's say we had another function. The less contrived version of this is, let's say you had a C function that you needed to call in here instead. Oh, apparently this alt-enter thing broke. Yeah, okay, that doesn't work anymore. Great. So the alternate example is you wanted to do, call the foo function instead, right? And the foo function has some, return type, and it has some argument type. And you call it with various arguments. But, it is, we don't have to do that for the example. But that's the canonical example. You actually want to emit code that calls some other external function. So we could, for example, go ahead and write, do a version of this that calls bar instead. And we could define that, and then we could go through and be like, oh, well, we need we need this for the baz function too. And you see this in all sorts of code, right? Like where people have the exact same thing copied multiple times. And any time you see the same thing copied multiple times out, you should get suspicious as a programmer and be like, there must be some way we can automate this. There must be some way we can write this fewer times. And so metaprogramming is the answer. This is how you go about writing this fewer times. So what we're going to do is we're going to write a for loop that iterates over a bunch of symbols. And we can see this pretty easily. We can just initially write, do this and see, okay, that just prints the symbols for us, no problem. But instead what we're going to do is we're going to do what's called eval. So eval is a macro that lets you put an expression inside right after the eval. And then inside that expression, what you can do is you can splice in some value that's from outside of the eval. So in this case, what we're going to do is we're going to splice in the symbol. And you do splicing with the $sign. So here's how it works. So what we're going to do is we're going to say, we're going to define the function. What did we write here? Func. Okay. Okay. So we're going to want to put a symbol here. Okay, so I'm just going to type this and hope I get it right. Oh, that's right. Sorry. Okay. So just to see that we're actually getting something different, I'm going to put a star in front of it. And we can see that these functions are actually now redefined. So what happened here is it went through and this is slightly complicated, but what you do is you take the string function, takes the string func underscore and concatenates it with sim, which is just a symbol, and creates a string out of the whole thing. So now you have the string func underscore symbol. The way you represent things like identifiers, names of variables, names of functions, names of anything in Julia is with symbols. That's what a symbol is. It's basically the way of, it's the abstraction for an identifier in a program, but as a just piece of data. So what you need to do is take that whole thing, turn it into a symbol. The $sign with parentheses basically says, splice this into this, this expression here, and give me then, the rest of it is just sort of normal stuff, except for here you get the string version of the symbol, which you then also print. You might be able to skip the string part here, because I think we print symbols just as the string of the symbol. And then the eval is basically what just says, I want you to splice this thing in here and then pretend that code was in here and actually evaluate it. So this is a shorthand way of generating a bunch of functions at the same time. So now we have, our, the good thing is no matter how many of these, we had, it's not any harder to actually define those. And so that makes it really nice if you want to, for example, in the case of binding a library, generate, I don't know, like 25 different function wrappers that all kind of look the same. The details of getting all of this sort of $ and eval stuff exactly right is a little tricky, but it's actually not that hard if you kind of get it in your head right. So the way to understand it, to go a little deeper, is that Julia has this property of what is known as homoiconicity. And this is from the Lisp lore. Basically, homoiconic, a language is homoiconic if the representation of code in the language itself is just a data structure in the code. And it basically means in Lisp it means that Lisp programs are represented as lists, which is the basic data structure of Lisp, which means that you can take a program and treat it as data and manipulate it and modify it, generate it, and then actually run that code at the same time. It's not quite as simple in Julia because we have syntax, but you can get at the data representation of Julia code pretty easily. So for example, you saw these sorts of things, in Doug's presentation. This thing is just an expression. So the colon parentheses is a way of quoting an expression. So it's a way of saying, I have some code, but I want you to treat it as data instead of evaluating it right away. So you do this, and what it does is it gives you an expression object. That is of type expression. You can see the names of the expression type is head, args, type. You can dump the expression, and what you can see is that it has these different fields. Expression has a head field, which in this case is the symbol call, because it's the expression is just a call to the tilde function. And then the arguments are the things of the call. The first thing in the argument is the thing you're calling, which is tilde. The rest of the things are the arguments, so it's A and B. The type field is not something you really have to worry about when you're generating code or manipulating it. That's actually used internally by Julia to figure out what types expressions can have when it's trying to generate code.
So what could have gone? What like single characters could have gone between the A and the B? Is it just like plus star?
Yeah, anything that's an operator that has syntax could go in there.
So what are the operators?
Well, I mean, the definitive source is that there's a scheme file somewhere that has all the operators. But in general, if you look in the documentation, there's.
When you're dealing with expressions, though, you do not need to know what are operators because at that point, that distinction is gone.
Yeah. So, for example,
you typed ABC. I mean,
the F of AB syntax is exactly the same.
Yeah. So you see that. Whoa, that is not what I meant to do. Okay. So. Let me just dump.
What I'm really asking is, I'm getting a sense, but I'm not hearing it clearly, so I'm going to ask it. I'm getting the sense that when you want a new operator, plus and times are sort of kind of busy sometimes. Tilde is the first thing you should think of? Because I'm getting that sense.
That's not what this is about. We're not talking about defining functions. We're talking about looking at the data structures that represent code. We don't really know, at this level, we don't know what these functions mean. They don't
yeah, the fact that writing A plus B like this is exactly the same thing as writing this. It's just a convenient mathematical syntax for applying the plus function to two arguments.
Tilde works the same way, and this is probably tangential to your main point, but it's still inside your example.
Yeah.
Yeah, it's also like you saw the deparse of the expressions,
right.
Y tilde A plus B plus C came back as
Yeah, so if,
colon, comma.
right. So the only reason I used the tilde in the example was because that's what we had already seen. But if you if you write something like, whoops, I need an extra parentheses. Yeah, so this comes back, and this is the way Julia represents this expression to itself. And so what's interesting about this is that you can construct these, but the quotation, this little like dollar, this colon parentheses notation, what it really is it's a convenient way to construct these expression objects, because obviously, you can make an expression object and just say, I want to have call as the head, and then I want to have an array of plus A and B in there. And that is exactly the same thing as writing, gives you the exact same object as writing A plus B. But because we already have access to the Julia parser, which is really good at generating these expression symbols, we have this colon parentheses thing. It's just a nice, easy way to generate expressions. But because you can construct expressions like this, you can very easily generate any sort of thing you want. So for example, you can do construct a block. Okay, so that's currently just an empty block. If we evaluate it, it does absolutely nothing. So the eval function takes an expression and evaluates it. So that doesn't do anything.
Is there something different between the capital EXPR?
Yeah, the lowercase is just a convenience function that doesn't require all the extra arguments. So it just assumes that they're nothing. So if you dump BLK, it's got no arguments, and it just fills in the any for the type. So, but this is something with a block as the head. So, what we can do here is, let's say we want to, so you can access the block args, and it's just an empty any array. But we can push stuff into it. So, for example, let's say we wanted to push. Okay. All right. So now that actually modified this block thing. So now block is actually a block that has one expression in it. So we can evaluate it. And it prints hello. You can also now, do that. Now it's an array of two expressions. If you look at the block when we print it, you see that it's now the same as a block that prints two things. So if we eval that block, we get hello and world.
You can do some of this with MATLAB with just creating strings and eval, but no access to a parser or anything.
Right. So that's sort of where it becomes better, is that you actually have this first of all, you have access to the parser directly. And the other thing is that you have access to these data structures. Like I have access to that args thing. I can apply all of the power of my programming language to manipulate that thing instead of having to construct strings.
It's a naive question, but is that representation what you refer to as ASTs?
Yeah, which is kind of a misuse of the word. AST is really something more internal to the. It's an AST? Yeah, okay.
Is a syntax tree.
Yeah, AST stands for abstract syntax tree.
Oh,
Abstract syntax tree.
For some reason it was asynchronous or something.
No, it's abstract.
Asynchronous.
Yeah, so an abstract syntax tree is basically the data structure that a parser produces after it's looked at your code and pulled it apart and turned it into expressions and a tree of objects. Okay, so that's a little bit about how you can create and manipulate expressions and objects and evaluate them. The eval, so this eval thing that I was saying, all that is actually just shorthand for saying eval quote and then putting some stuff in the middle. and that just kind of looks ugly a lot of the time. So we made a macro for it. And the reason you need to do this is, let's say you have some symbol that you say equals foo. You can't just splice foo into the middle of some function. You can't just say, f of whatever equals foo of something. That's just not going to work, because you can't splice in the normal course of just like writing code. So essentially what you need to do is you need to put the eval quote around it, and then inside the quotes you can do whatever you can actually splice things in. So that's really what's going on there. So the one final thing that you'll often hear a lot about that in metaprogramming is macros. And macros are, once you know about expression objects, pretty straightforward. So basically what a macro is you just want to, a macro invocation in Julia looks like this. You have some macro, and then you have some expression, another expression. You can have 0 or as many of these as you want. And what this gets turned into is it actually calls the macro expander function, which you define using the macro keyword. And as many arguments as you expect the macro to take. And then you put some code in here, and this is what's called the macro expander function. So what this does is it actually takes these expressions at compile time. So when the parser sees this, it looks at these expressions, parses them, passes them into the body of this function, evaluates this, and then whatever expression this returns gets spliced into the code at this original time. And so the reason that's useful is because you can basically create your own syntax, because this is taking some little snippets of code, piecing them together somehow, and then producing the code that you actually want to run. The name macro was used in C also for what the C preprocessor, which basically does textual stuff. The difference there is that in the C preprocessor macro, you don't have access to the entire functionality of the programming language. And you don't have access to the parser for the programming language. But so let's give a simple example here. So actually, a nice, easy example is the time macro. Nano base utils. Okay. So let's look at the time macro. So the time macro right here is pretty straightforward. What it does is it takes an expression. Whoa. So the time macro takes an expression, and what do you want to do if you want to time an expression, evaluate an expression? You want to take the time beforehand, and you want to take the time after, and then in between you want to run the thing. So what the time macro does is it takes an expression and instead of replaces the macro call with that expression with this whole block. And the block says, local t0 equals time. Then I want to save the value, and it splices in the actual code for the expression you got. So what ends up happening is you get that actual code, then take the time again, and then print elapsed, and then return the value of what the expression evaluated to. So let's see an example of that in action. Okay, so I time the sleep function. It returns 0, and it prints the time that was elapsed. Okay, so let's what is it called? Macro expand. Macro expand. Oh, of course it is. Okay, so what I'm going to do is I'm going to, just to see how this works, I'm going to have an expression. This is the expression form of that call, which is just an expression, and you can look at it and say, you know, what's the head of this? It's a macro call. What are the args? The arg is just, you know, the name of the sleep of the time macro, and then the expression sleep. So that's how that expression looks to Julia. Macro expand is going to expand macros in it so we can see what it actually ends up looking like. And so this is what happens. This is what Julia takes. It takes that expression, and when it's parsing it, it actually goes in and applies the macro time and substitutes all these things in. And so what you can see is that it does some cleanup, so it makes sure that the time function you call is the one that was in the context where the macro is defined. Sleep is whatever sleep is in the current context where you're calling it. Then it does all of this, and you see the names get sort of munged so that you don't accidentally clobber anything that, you know, was in the current namespace, and that's all done automatically for you. And so then you can evaluate this, and it does exactly what that's exactly what happens when you actually run the time macro, is that Julia is internally expanding the macro and then evaluating the resulting expression. So macros can be handy, for example, for doing things that you can't easily do with time. For example, you can't do this as a function because, you know, if you wrote something like time sleep, well, by the time the time function gets a value, the sleep has already happened. So it's, you know, way too late to actually do anything. You can't, you know, time the time before or time the time after. You actually have to transform the expression. So are there any questions about this? It's a little meta, but.
What was the function of the ESC?
Oh yes, yes, that is a very good point. So there's this slightly hairy issue that in macro programming, which is that there's the context in which the macro is defined, which in this case is in the base of base code of Julia, and then there's the context in which you evaluate it, which might be in the REPL you're in a module called main, or your own program, which is doing whatever, and it's possible that when you're defining it, we want time to be referring to the time that's in base. We don't know what you've defined time to be in the context in which you call this macro, but we don't want everything to break. So this is the issue of macro hygiene. Basically, what hygiene is about is making sure that all the things refer to what they're supposed to refer to.
If you have your own time function or a variable called time or something, this will still work the way you expect.
Right. And that's what the expansion is about. So the escape, what the escape does is the escape says, this expression, I want you to escape it so that it actually means what the user meant it to mean. So things that are unescaped get automatically translated so that they refer to things in the defining context. Things that are escaped don't get translated and are allowed to pass all the way through to the caller's context and modify or refer to things in the caller's context. So in the typical usage like this, you get an expression from where the macro was called. You want to escape it so that is then evaluated in the context in which from which it was passed to you. So you can see this in the macro expand because sleep here is unaffected, right? Sleep is just not translated at all. Time is translated because we stick the base in front of it. So that's sort of the difference there, is that if, let's say we redefine this. Okay. So, let's make sure that works. Time, one should still work. So let's say we didn't have the escape. what would happen now when we macro expand this? Oh, this is probably calling the other time, right? I'm going to call this my time.
Because you define, this is now a macro, the definition context is main now.
Oh, yeah, yeah. Oh, yeah, so now, right, this doesn't have to be rewritten because everything's in the same context.
Mm-hmm.
Yeah, I'm not going to recompile Julia just to demonstrate that. But you could do, actually you could do this, module.
You're missing one end.
Yeah, I'm intentionally missing one end because the shift enter business is broken right now. Okay, so there I just defined a module and exported the myTime macro. Okay, so what? Oh, yeah, okay. I need, why does that not refer to base time? Jeff, any idea? Anyway, kids, don't do macro programming on the fly.
All I can tell you is that this is doing something that will do the right thing. I mean, it doesn't have to, it doesn't have to do any, it can produce anything it wants as long as it behaves right. That's
Yes.
all I'll say.
All right, so, all right, hopefully that clarified more than it obfuscated. The chapter in the Julia manual on metaprogramming is actually pretty clear. Probably clearer than this presentation. But so if you're interested in this and you ever find yourself generating code for whatever reason, consider metaprogramming.